Hi everyone, my name is Hằng Dinh from IU South Bend. In this video, I will explain one basic but very important feature of Golang, that is functions as first-class values. For the materials of this video, I recommend you to read the Go document at the links here on this slide, and also chapter 5 of Donovan's and Kennigan's textbook. What are first-class values? In programming languages, first-class values are those that can be assigned to variables and passed as argument to a function and returned as values from functions. For example, integers are first-class values in every programming language. You can assign an integer to a variable, as in x equal to. You can pass an integer as argument to a function and return an integer from a function, as in this example. Functions and arrays are not first-class value in many languages, such as earlier versions of Java. But many modern programming languages, such as Go and Python, support first-class functions. So in Golang, functions are first-class values. Here is an example of how a function in Go can be assigned to variables. In this example, we defined a function square that takes one integer as argument and returns an integer value that is the square of the argument. The statement f colon equals square declares a variable f and assigns a function square to f. Here is an example of how a function is passed as arguments to another function in Go. This is the definition of function compute, which takes one argument named fn. But the type of this argument is a function type. Like other values, function values have types. A function type is written similarly to a function header, but without function name and without parameter names. The function type in this example is the type of any function that takes two float64 arguments and returns a float64 value. Parameter fn is of this function type. So fn is a function that takes two float64 arguments and returns a float64 value. This means that we can call function fn passing any two arguments that can be converted to float64 and get a float64 values. The value returned by function fn is then returned by function compute in this example. An example of how a function is returned as value from another function will be shown later. As shown in the previous slide, a function value may be called like any other function. Also, like values of other types, function values can only be assigned to variables of the same function type. For more examples, let's consider this program. In this program, we define three functions besides function main. The first two functions, which which are square and neg, both takes one int argument and return an int value. So these two functions have the same type. The third function is prod, which takes two int arguments and returns an integer value that is the product of the two arguments. So prod has the different type than functions square and neg. In the main function, we declare variable f and assign a function square to f in a short declaration form. So variable f is of the function type that is the same type as a function square. And because f is the function values, you can call it like any other function. Okay, and but at this point, the function value f has the same value as function square. So calling f of 3 is the same as calling square of 3, which returns the square of 3, which is 9. And then we assign function neg to variable f. This assignment statement is legal because f and function neg have the same function type. Okay? And then now f has a different value which equals a neg. So calling f of 3 is the same as calling neg of 3 at this point, which returns the negative of 3. And then you can also print out the type of variable f as in this printf statement, and it display fun of int and int. So this is the function type of the variable f. And now if you try to assign function prod to f, you will get an error because function prod is of different function type than variable f. So you cannot assign prod to variable f. Like any other data type, function types also have the zero value. The zero value of a function type is called nil, which is the same as the zero value of a slice type. Calling a new function value causes a panic, which is a runtime error. For example, after we define variable f to be of the function type that takes one int argument and returns an int value, then f is a new function value. So when we call f of 3, it causes a panic. After we assign function square, which is of the same type as a variable f, then function value f is not nil anymore. Function values may be compared with the nil value. For example, you can compare if function value f is not equal to nil as in this if statement. But function values are not comparable, meaning you can't compare between two function values except when one is nil. For example, comparing if function value f is equal to function square in the second if statement in this program will cause an error. Since function values are not comparable, they can not be used as keys in a map. For example, if you define a variable m to be of this map type, where the key type is a function type, then you can also get an error. In examples of Go programs we have seen, we've always given every function a name. Those named functions can be declared only at package level. You can't declare a named function within another function. But we can use a function literal to denote a function value within any expression. A function literal is an expression written like a function declaration, but without a name following the func keyword. For example, the expression highlighted here is a function literal. It is written exactly the same as any other function declaration or function definition, but without the function name between the func keywords and the parameter list. Okay? It still has the parameter names as usual, but there's no function name. So this is a function literal. And a function literal is a function value. So you can assign it to a variable. Okay? So in this example, we assigned this function value to a variable named HighPort, and this is the short declaration form. So we also declare this variable to be of the function type that takes two float64 parameters and returns a float64 value. The value of a function literal is called an anonymous function because it doesn't have a name. Anonymous functions lead to the concept of function closure. A closure is a function value that references variables from outside its function body. In this sense, the function is bound to the referenced variables. And this is why the function values are not comparable. Closures are often created using anonymous functions or function literals defined within another function. For example, the highlighted code fragment in this program is a closure, which is an anonymous function defined within function adder. Function adder takes no argument and returns a function value that is of the function type that denotes any function taking one int argument and returning an int value. The function value returned by function adder is a closure because it references adder's local variables sum, which is outside the body of the returned anonymous function value. Its closure is bound to its own sum variable. To demonstrate this phenomenon, let's consider the code in the main function of this program. Here we define two variables, post and neg, and assign a function called adder to each of them. Each call to function adder has a local copy of variable sum, and the closure returned by the call to adder is bound to that copy of variable sum. So the closure assigned to variable post is bound to its own sum variable, and the closure assigned to the variable neg is also bound to its own sum variable. Its closure can still access its own sum variable by adding its argument to sum, even after the function adder has finished execution. So after this calls to function adders, those calls have finished execution. And as you can see, when we call post of 1, it adds 1 to the sum variable of post, modifying that sum variable from 0 to 1. But the sum variable of neg is still 0. And when we call neg of -1, it adds -1 to the sum variable of neg, modifying that sum variable from 0 to -1. So the output of pose of 1 would be 1, and the output of neg of -1 is -1. And when we call pose of 2 and pose of 3 later, it adds argument 2 to the sum variable of pose, modifying that sum variable from 1 to 3 because 1 plus 2 is 3. And then from 3 to 6 because 3 plus 3 is 6. Similarly, when we call -2 and when we call neg of -2 and then neg of -3, it adds -2 and then -3 to the sum variable of neg, which is independent of sum variable of pose. So the result of neg of -2 is -3 because it adds -2 to -1, so that makes -3. And then when you add -3 to the sum variable of neg, it will add -3 to the current value of that sum variable, which is also -3. So the result is -6. Anonymous functions can also be recursive. But how do we define a recursive anonymous function? When a named function requires recursion, we simply call itself by name. For example, to define function sum that takes an integer n as argument and returns the sum of the first n positive integers. We use the recursive formula sum of n equals sum of n plus 1 plus n when n is positive. To implement this recursion, we simply have the function sum with a parameter n, call function sum by its name with argument n minus 1. When an anonymous function requires recursion, it cannot call itself by name because it has no name. So instead, we first declare a variable and then assign the anonymous function to that variable. The assignment must be separate from the declaration of that variable. Here is an example of how we define recursive anonymous function. This anonymous function is defined in the function main of our program. It does the same job as the named function sum in the previous slide. That is, it takes an integer n as argument and returns the sum of all integers from 1 to n. But here we first declare variable sum to be of the same function type as the anonymous function. Okay. Then we assign the anonymous function to variable sum. So this anonymous function is the same as the definition of the function sum in the previous slide, except that there's no function name here. And the assignment of the anonymous function to variable sum must be separate from the declaration of the variable sum. And so in the body of the anonymous function, we can also use the sum of n minus 1 in order to implement the sum of n. And so when we print out sum of 3, it will display the sum of 1 plus 2 plus 3, which is 6. And when we display sum of 4, it will display the sum of 1 plus 2 plus 3 plus 4, which is 10. Recall that functions are first-class values in Golang, so they can be passed as arguments to other functions and can be returned from other functions. The functions that take a function as argument or return a function are known as higher-order functions. Higher-order functions let us parameterize our functions over not just data, but behavior too. We have seen examples of higher-order functions before, such as function compute and function adder. Function compute takes take a function as argument, and function adder returns a function. The standard libraries also contain many examples of higher-order functions. Function map in the strings library is one such example. This is the header of function strings.map. It takes one function and one string as arguments and returns a string. The function argument is any function that takes one rule as argument and returns a rule value. Recall that a rule value represents a character. Function string.maps applies the function argument to each characters of the string argument and joining the result to make another string which is returned. Here are examples of how we call the function strings.map. In the first call, we pass a function add1 as the function argument and pass abc minus 12 as the string argument, where function add1 is defined as taking a rule value as argument and return the rule value equal is argument plus 1. So add1 will turns capital A to capital B, little b to little c to little d, the minus character to the period character, the number 1 to number 2 character, from 2 to 3. So the string returned by the first call to strings.map is the string bcd.23. In the second call, we pass an anonymous function as the function argument and pass the same string abc minus 12 as the string argument to function strings.map. This anonymous function takes one rule value as argument and returns a rule value equal is argument plus 2. So it will shift every character 2 positions up. In particular, capital A to capital C, little b to little d, little c to little e, minus size to forward slash 1 to 3, 2 to 4. Thus, the result of the second call to string.maps is the string capital C, D, E, forward slash 3, 4. That's the end of this video, which is also the last video covering basics of Golang. After this video, you should be able to write simple to moderately complex Go programs. Thank you for watching, and I'll see you again in my next videos.